Hey everybody, so here today to go over a demo of writing a parser. TR recently wrote an article called Just Write the Dang Parser, and writing parsers is fun. It's kind of like one of these code kata things. It's a nice exercise that follows some very straightforward patterns, and it's also kind of a fun coding problem in general, and parsers are often quite useful. There's some automated parser generators like Flex Bison or Antler, but often writing recursive descent parsers is an enabling capability to have, and I've used them several times in my coding career, so they're kind of fun to learn and fun to use and nice to know how to do. So hopefully you can follow along with this if you're interested in making your own parsers, recursive descent parsers. And we'll try to live code something up, expression parser. Alright, so we're going to try to do the TDD style thing here, where we create a file, we will define a test, parse 2 plus 3, that's a basic expression that we're going to do. So our whole program is just going to be a single expression, which is this string. We're going to parse that, we're going to get an AST node that results, right? So a parser fundamentally is taking things that are written as text all the way to a structured form, which is a AST or a parse tree. AST is abstract syntax tree, so it might sometimes have some simplifications relative to a raw parse tree, but AST is kind of a blanket term. So we're going to parse the program. Ultimately, the whole parsing routine will scan the characters into tokens and then structure the tokens into a parse tree. And then we'll be able to assert some things about our expressions. So usually the way that people represent these AST nodes, this tree that represents the grammar of the original program, is with subtypes. So we're going to kind of do an object-oriented sort of thing today. In Python, there's fun things you can do with a functional style approach and iterators, but we're going to try to keep it a little bit vanilla and do object-oriented style today. So our expression should actually be an instance of add in this case. And add is going to have the two children, so we're going to say that the first child is a AST number, which is also going to be a subtype of expression, and it's going to hold 2, and then the other child is going to hold the number 3. And so compile this. Okay, and now our pytest watcher is able to run in a loop. So parse is not defined. That makes sense. So we're going to define some entry point parse that takes the program text, and since it's an expression parser, it's just going to produce expression. We're going to stub this out, get our error. Expression is not defined. Stub that out. Okay, now we get our not implemented error. Okay, so fundamentally, there's 2 steps involved in the parsing process. The characters are converted into tokens, which are a more structured form that identifies like the atoms that are in your grammar. And then the tokens are structured further into a tree that is representing the grammar that your programming language has. And so what we can do is we can create a scanner object, and that's going to structure the characters into these token objects. And then we're going to create a parser, which is going to take the tokens that come out of the scanner and structure them into the tree. And then we are going to return the AST that results from the parsing process. So our test is not happy because these things are not real. There's no scanner. The scanner needs to be able to take the text, which is a string, and store it internally. And so the scanner basically keeps a position like a cursor of where it is inside of the text to figure out where it should give the token from next in the stream of characters. So abstractly, the text is just a character stream. It doesn't actually have to be like all in memory at the same time. But just for simplification, we're just going to keep an index into a big in-memory string. So our index at the start is always 0. And then we need to create the parser that is the unique consumer of a given scanner object, because if there were multiple parsers using the same scanner, that would not be good. And then we need our parser to be able to parse whatever the thing is that it's ultimately grabbing from the scanner and produce an expression AST node or always an error. And normally we'd make comments for all these things, but because we're live coding it up, we'll just walk through the code. Okay, so now we're in the parser team, and the parser is saying, I don't know what to do. So fundamentally what the parser has to do is it has to grab a token from the stream of tokens that are present. Now here we can say, hey scanner, may I have a token please? And I'm going to call it pop t just to indicate that we're popping a token, because sometimes it gets a little confusing between popping characters and popping tokens, and so pop t is just a cute little way of reminding us whether we're popping characters or tokens. And so it says the scanner doesn't know how to pop a token. So we're going to teach it. So something happens and we pop a token. And so we need to define what a token is. And so a token fundamentally is a thing like a number or a plus, one of these fundamental atoms that comes out of the character stream as a more structured form. So it's going to have a kind. And it'll also have, we'll also say what the original text that kind came from was. So you could think for a number, the kind would be number, but you still want to know what the characters were that made up the number. So let's set the value there. And token kind needs to be an enum. And let's not say what's in there yet. Import enum. Great. So now we say, okay, I have pop t, but I don't know what to do. So what we're going to do is we're going to look at the first character in the character stream. And that character might be something like a plus, in which case we know that we want to return token kind dot plus, and the string is just the character that made it up. Okay, so now it's saying the scanner doesn't know how to pop a character. So we'll define pop c, that pops a single character, and this is going to use the ability to peek at a single character at the current position. So that's just accessing the text at the current index. But then in order to pop it, we'll use the ability to peek it. We'll advance the index so that we're pointing at the next character in the stream, and then we're going to return c. So obviously this, if it ever goes out of bounds with the index, will throw a index out of bounds exception. Okay. So now we get to the point where, in our test example, we didn't have a plus at the very beginning. We had the number 2, so it hits this not implemented error. So let's just define a little test that make sure we can scan the plus operator. Scan plus. And so we're going to create our input text is just plus, so we'll do scanner of the whole program is just plus. And when we pop token, we should get a token that is token kind.plus with the plus as the text. So let's see what it thinks about that. Okay, so although this test is still failing, attribute error from the previous test. Okay, so here we want to define plus, and we'll give it the value plus. Okay, so now it's saying I can't pass this assertion because you didn't define what equality means for the token object, which is a little bit of a bespoke error message, but that's ultimately what it's saying. And so we're going to say that this kind, we can only be compared to other tokens, and self.value is other.value. What's it think about that now? Okay, it says I don't know what a token is because you're defining it right now, so we have to use this Python string syntax for the type being currently defined. Okay, and so we found one error, but the other one passed. One passed. Oh, EQ is incompatible with supertype object. Defines it as object, I see. Okay, so we need to say return is instance other token and this. Okay, 3 passed, 1 failed. That sounds pretty good. So now it's just complaining about our test parse 2 plus 3. So that test is passing. That's great. Okay, now that we know how to parse plus, now we want to see if we can also handle characters that are digits. So if the character is a digit, let's assume it's a single digit character to do the good TDD thing. And we'll just say, okay, here's your 1-digit number. And let's not do else after returns. Let's do early exit returns. A little bit cleaner that way. Okay, I don't see number as an attribute on token kind, so we'll add that. Okay, very nice. So now we're up to parse, and we were able to pop this token out. It's presumably a number that holds 2, and then we raise a not implemented error, because what do we do with that token? We have to somehow turn it into AST nodes. So first we can do parse number self, and this is going to return an AST node. Let's say it's a number AST node. So sometimes you're just taking a token and basically wrapping it up in an AST node that says like, yep, I'm a AST node that just wraps up this kind of token. And that's what we're going to do here. So to parse a number, we're basically just going to create a number AST node that, so we're going to pop this token. We're going to check in some fashion. We want to raise really a parse error if this thing is not a number. So we could say if token.kind not equal to token kind.number, raise parse error. And so we're going to need to test this path and say expected number got token. And we'll use a format string for that. Okay, so we're going to need to test that path. But otherwise, we'll just have the number wrap up that token. It doesn't know what a number is, so we'll create a number that subclasses an expression. We could have the number take the token directly. You can sometimes put the tokens directly into the AST nodes. There's a bit of a layering effect that happens if you do that, but it's generally fine. So we'll just say that the number just holds on to the token, and someone will ask it questions eventually. Well, actually, the way that we defined it in the test, we just took the string of characters. So why don't we do that? Why don't we just say the value is a string of characters, self.value equals value. And actually, we could just use a data class for this. So data classes dot data. Oh, but it has to subclass expression. Yeah, so let's just do it this way right now. And so we're going to need to define a quality for the test. And then other has to be an object we learned. And so we say is instance other number and self.value is other.value. So this is a little bit unduck typey to not just test the value, but that's okay. We don't mind being a little bit unduck typey here. Okay, so now we're back to the point where we're raising not implemented error after popping the token. That's because we need to switch the parser to return parse number, because that's right now the only thing that we know how to parse. Okay, and so the token has no attribute kind. It's actually underscore kind, so we can do a read-only property just to make sure that we don't accidentally mutate it anywhere that returns the token kind as kind. Okay, now this is pretty cool. So now it's getting up to the point where it says, hey, add is not defined. So you have expression, right? But we didn't make this subclass add. So add itself is an expression. And what does add need? It needs a left-hand side and a right-hand side expression. And it's going to store those internally. But what we could do is we could have the expression node actually hold all of the child nodes, AST nodes. And that'll make some things easier because, you know, there's this abstract concept that an expression node will have some sub-AST nodes that it has as children. So it'll make making some routines in the future easier, probably. All right, so our children is, let's say it always has to be a tuple of these expressions. And this is how you annotate that in Python. And so children, since this is a tuple, I'm not too worried about making anything defensive. But I do have to do from typing import tuple. Okay, great. So now it's saying, ha, I got a number. I didn't get an add. So an interesting thing here is that when we parse the program, right now nothing guarantees us that the scanner is extinguished when the parser is done. So why don't we just add an assertion here that the scanner has gotten to the end of file when the parser thinks it's done. Otherwise, the parser didn't pop something out of the character stream. So really, we should have extinguished all the characters. It's a good sanity check there. So we need to define what at end of file means to the scanner. Okay, so we're at the end of file if the length of the text is equal to our current index. We could be a little bit defensive here and say if the index is greater than equal to the length, but maybe what we'll do is we'll just assert that self.index is always less than or equal to the length of self.text. Okay, so now this assertion is failing because remember we popped a number out, but we didn't pop anything else out, and that's because our parse routine is just parsing a number. So once we've parsed a number, let's call this like a term. So there's term, and then the add sign, and then another term. So here we could do the popping of a token out of the token stream to see, or the peeking at a token in the token stream. It might be at the end of file after a number. Just a number is an expression, right? But we could also see a plus sign, which would indicate that we should look for more things, because you can't just do a plus and then stop, right? So here what we'll do is we will pop a token out of the stream. Actually, we're going to peek at it because we don't know if we want to pop it yet. So look ahead is peek. And so if the look ahead kind is a token kind plus, then we want to pop another term too. Let's call it the right hand side. And we'll parse another number. And then we'll return token kind, then we'll return add, where this is a number AST node, and this is a number AST node. So both of those are expressions, so we can do term and right-hand side. So we could call left-hand side number equals term. Okay, and then here we will just return the term. If we didn't see a plus sign, it might have just been a number, so then we just return the term. So we should really add that as a second test case, is parse test parse 2. So if we just do 2, then we should get an expression. The expression should be a number, and the AST node should be just the simple number 2. Okay, so now it's saying, you did not reach the end of the file. And this is for which test case? 2 plus 3. So, I'm sorry. Once the parser has run, we should have reached the end of the file. So we say result, which is a expr node, and then we return that. So once we finish parsing, that's when we should be at the end of the file. Okay, parser has no attribute peek. Okay, so when we're grabbing stuff from the scanner, sometimes we just want to look at what is there. This is called look ahead. And we don't necessarily want to pop it destructively from the token stream. So the scanner conceptually is providing us a in-order sequence of tokens, and we can look at the one that's there, or we can pop it out. And those are the two things that we can do. So I'm going to call this peek t to just remind us that what we're peeking at is a token. And so in order to, since scanner only provides us with pop, what we can do is we can just buffer up, hold on to what's called a look ahead token, which is an optional token. It's going to start off as none. And so this one's always going to give us either the next token in the stream or raise end of file exception, which end of file exceptions we'll come back to later. But basically what this is going to do is it is going to say if we already have a token buffered up and look ahead, well, that's the next token in the stream. Otherwise, we have to go to the scanner. We have to pop the next token out of it, and that becomes the look ahead. That's the thing we're buffering up, and then we return that. And so now scanner has no attribute pop. Scanner, what did we call? Oh, we called it pop t. Sorry. Pop t. All right, great. So now we're trying to assert that some number object is equal to number 2. But we didn't define a repr for this, so it looks a little ugly. So let's define a repr. self stir return number self dot underscore value. And repr that. Okay, so our EQ is somehow not defined exactly right. Because those two things look exactly the same. Oh, I see. So number is actually getting past a token object. So then the mypy based test may also be failing. Optional is not defined. From typing, import optional. Aha. Line 83, argument 1 to number has incompatible type token, expected string. So that was because we changed our mind and we said that we were going to use the string to construct the number. But then it says the token has no attribute value, and I think it does. It just wants to keep it private, so we'll make a read-only version. Def value self-return string. Okay, great. So now we are getting our end of file reading, peeking past the end exception. So there's a couple of different ways to deal with this. So you could only look before you leap. You could only peek at the character stream when you know you're not at the end of file. Or another way to do it is to return an end of file sentinel token once you've reached the end. And there's pros and cons to both ways of doing it, but for now what we're going to do is we're going to say peek C, so peeking at a character, that is going to fail. But when you pop a token, if self.atEndOfFile, right, then we are going to return a token, that's token kind end of file, and that's the end. Okay, and so now that we do that, it says parse error is not defined, because it's parsing and trying to parse a number and then getting the end of file presumably. But parse error is not defined, so let's define a new exception. Actually, the default exception constructor should work for us. Okay, so found no issues. Oh, so that was coming from mypy that it said parse error is not defined. Okay, so now we've passed that test. Cool. Well, that's a very basic expression, so let's see. Let's try to make the grammar a little bit more complicated in the next part of the video. Okay, so there's one bug in the previous part of the video that I couldn't let go and move on to the next video without addressing. So you remember how we created this look-ahead token, which when we peeked at a token, we populated this look-ahead field. And then when we're popping the token, this was the part that we forgot to make symmetrical. And so the law of Demeter is this kind of programming recommendation that says, instead of reaching into member objects and calling methods on them, if they have interesting invariants, try to keep local members that maintain the invariance. So along with peekt, we really should have something called popt that also knows about look ahead. So instead of reaching into self.scanner and doing things like here, we should be calling our helper popt that lives as a member of the parser type. So what popt is going to do is it's actually going to, just like popc uses peekc in the scanner, it's going to use the facility from peekt, so it's going to make sure that it can peek at a token at the head of the token stream. And that means that look ahead must be primed up, because this always populates look ahead on all paths, right? That's basically the point of peekt, is I'm going to look at the peek at the next token, I'm going to shove it into the look ahead field. So now we're going to assert that it actually is populated, and then we're going to clobber it, clobber the storage that says this is the peeked at token, and then we're going to return that token from popt. Okay, and so now that we've done this, so parse number is popping a token from the stream, and parse number here is popping a token from the stream. So when we peeked at this look ahead token, we determined it was a plus. now we know, yeah, that actually is something we want to consume. So here we'll actually pop it off the stream. Okay, so now everything is kind of back to normal. So before, when we were peeking at stuff and populating the look ahead, it was not working properly. And look ahead's a little bit of a complicated piece of state to test. So as you create more test cases, obviously it would find a bug like that. But working backwards of, when are we going to look ahead at which token and then what state will it cause, is a little bit complicated. So just because we're able to spot the bug easily by inspection, we'll just fix it here. But adding further tests and more comprehensive tests also would have demonstrated that there was a bug there. So yeah, we'll make the grammar more interesting and expressive in the next video. Basically here, we're just supporting a very basic grammar that says, an expression is basically an add or a number. Let's say a term. A term is just a number in this world right now, and then an add is a term followed by the plus symbol followed by another term. This is basically the grammar we're implementing right now, but it's very easy to extend this form to add more things. And you can see that the basic form of this, it's called an extended BNF grammar, Bacchus normal form, Nauer form, is reflected in the code here, where the first thing we do is we parse out a term, and then we look to see if there's a plus. This is kind of discriminating between whether we're going to look for another term or whether the term that we saw at the top level of the grammar is exactly what we're going to return. So next video we'll add a bunch more things.